try to cover a few issues, as you can see here. Hope we have enough time for everything. Of course, I will not give you all the mathematical details. It's impossible in a presentation. But there's few papers that you can look. Those are the last two ones. Okay. So let's start with a preface. And this is, of course, you all know, nobody could find dark matter. People have been looking for 40 years, and nothing has been found. And therefore, MOND is an attempt, maybe the first, but now here it's not the first, to solve the standing problems of gravitation at the large scale, not by postulating a new type of matter or particle, but by looking more deeply at the phenomena of gravity. And gravity, as Einstein taught, is nothing but the structure of space-time. So we have MOND, which can be modified Newtonian dynamics, or MOTI's new dynamics, whatever you like. And what is characteristic of the theory is acceleration. So large acceleration, we are in the Newtonian regime, and small acceleration, we are in the deep MOND regime, and in between there is interpolation. Now, acceleration is a very interesting parameter to choose because it's a second derivative. And we will see later the second derivatives appear also in retardation. Here's another thing to remember, Occam's razor. And this is William of Occam, a medieval scholar, and he taught that plurality is not to be posited without necessity. So you don't multiply complex causes to explain things when simple ones will do. And this is also called the law of parsimony, or in Latin, lex parsimonia. This was, of course, repeated also in Newton's Principia. But let's put it in the words of the master. It can scarcely be denied that the supreme goal of all theory is to make the irreducible basic elements as simple and as few as possible without having to surrender the adequate representation of a single datum of experience. This is Albert Einstein in Oxford in 1933. 33, yes. Okay, let's look at the facts. We have big physical systems, galaxies, clusters of galaxies, maybe the entire universe. They have many tens of thousands of light years, of course, much bigger in clusters of galaxies. Thus, any change at the galactic center will be noticed at the rim only tens of thousands of years later. What people are doing in the galactic center, we will never know. It will take too much time to reach us in our lifetimes. Those retardation effects seems to be neglected in naive galactic models used to calculate rotational velocity of matter in the rims of the galaxy and surrounding gas. The second fact is, of course, the strange rotation curves, where what Newton teaches us appears to contradict observation. Well known. So let me ask if those two facts are connected. The short answer, I think, is yes. This is the graph of M33, the Newtonian curve, what correction needed to be added by retardation. If you add them both up, they fit perfectly to the rotation curve that you see. Let's go into the theory. General relativity, we have to solve the Einstein equation, Einstein tensor, and then we have to calculate the geodesics in order to find trajectories of particle. T mu nu is defined by the method. This is the popular T mu nu of an ideal fluid. The simple equation hides very high complexity. R depends on the affine connection. Affine connection depends on the metric. Everything is hopelessly complex. But is it? The answer is that for most cases, and galaxies are included, it is not necessary to solve the full Einstein equation, but only a linear approximation to them, as only weak gravitational fields are involved. Of course, there are exceptions. Compact objects, black holes, the very early universe, the Big Bang, we have strong gravitational fields, and one needs to solve the exact Einstein equations. This remark was made to me years ago by Donald Lindenberg, which was a close collaborator, and unfortunately is not without for a few years. So I would like to thank the late Professor Donald Lindenberg for this very important observation. And now to the linear approximation. You take G, you write it as a perturbation. You write the perturbation around the flat metric eta, and you call it H. H must be very small than 1. With H you define an H bar, you plug it into the equation, and you get this quite simple equation. The Lambertian of H bar is proportional to T mu nu, and of course you have to choose the right gauge to get this equation. And then you solve it. The solution is well known. It's a retarded solution, and once you know H bar, you can calculate everything else. You can calculate H, you can calculate the affine connection to first order, etc. When you come to the geodesic equation, since the affine connection is linear in H, U mu, U nu, the term that appears is 0th order in H, and this means just those simple expressions, and it becomes even more simpler when the velocities are small, and they're usually small with respect to what is needed. So you put everything in the geodesic, and you get something which looks very much like Newton's law. You can define the potential. There is no forces in general relativity, of course, but you can define potential is just H bar 0, 0, and the gradient of the potential, you call it a force. And this is the potential, and it seems very much like a Newtonian potential, and of course it is a Newtonian potential where rho is static. But of course it's not a Newtonian potential where rho depends on time, and this is what we want to look into it. As we mentioned, retardation probably cannot be neglected on galactic scales, and the density is not static. And the possible cause for this is the mass accreted for the intergalactic medium into the galaxy. Something like that. Okay, so let's look beyond the Newtonian approximation. We can make a Taylor series in R over C, we keep only terms to the second order. I mentioned that it's not a requirement that we make this expansion. We can solve it numerically without expansion, but this is, in this way, we more easily get results. We will talk about this later. Okay, plug it in the potential, you get 3 terms. This does not matter because the gradient of this is nothing, and you have just a Newtonian potential and the retardation correction. So you have a Newtonian force and a retardation force. Now, the Newtonian force goes as 1 over r squared, meaning that it's very strong at small distances. This does not depend much on distance, and even if it's initially weak, it will become later strong when you are far away. Okay. So this means that there is something like a retardation distance, meaning that if you're at very small distances, you're in a Newtonian regime, and when you're at large distances, you're in a retardation regime, which is something like the deep MOND regime. And if you are far away from the main mass, the equation becomes even much simpler. Big R is like a small r, you can pull it out of the integral, and you just get a second derivative of the mass. Now, pay attention that retardation can be, or retardation forces can be repulsive or attractive. It depends on M double dot. Okay, so it can be a positive M double dot or a negative M double dot. My favorite scenario, mass is accreted into the galaxy as it is formed, but as we have more, we have less, I would say, gas to accrete, the second derivative is negative, the rate of accretion becomes smaller, and therefore we have an attractive force. Now, when is retardation important, and when can we neglect it? Okay, let's suppose we don't know about retardation, so we say there is some dark matter that is doing the stuff. So we have this equation, and then we remember that really there is no dark matter, or we don't believe in dark matter, so we equate those two terms, and we see that what we thought was dark matter is just r squared over 2c squared times the second derivative of mass. And from this you can calculate the density of the dark matter, and it goes like 1 over r, and this is what Corbelli and Salucci are telling us. They say r to the power of minus 1.3, but it's close enough. Now, let's look at mass conservation. We have the continuity equation, we take a derivative of it, and we get an equation for the second derivative of the mass. And this can be using Gauss theorem, you can integrate over a large sphere, you get something like this. You divide by the mass, and the expression is in the order of magnitude of v over c to the square times r over 3 distance scales, which are connected to the gradient of the density, the gradient of the velocity, and this is called the dynamical time scale. It's v squared derivative t to the v. So in galaxies we usually have v over c 10 to the minus 6. So in order to have large retardation effects, we need r over l over the gradient to be 10 to the power of 6. You can write it in a different way. And here I would make a connection to MOND. You can have 1 over LT, which is just the sum of all those typical scales. And when L is small, the smallest L, of course, is the most important in this respect. So The retardation force over the Newtonian force is of this order of magnitude. Now, in MOND, we like to look at acceleration. So let's put this condition in terms of acceleration. The acceleration we take as v squared over r, and this is the fraction of the retardant force over the Newtonian force. And if you put this in the inequality, it looks like this. So you can write as a term of the acceleration must be bigger than a critical acceleration, which is FR c squared LT over r squared. Now, AC, the critical acceleration depends on r to the minus 2. So this means that the inequality will be satisfied more easily for larger r. Thus, dark matter effect can be interpreted in terms of acceleration as MOND postulates. However, acceleration does not need to be small or equal with respect to A0 in order to have a dark matter effect. Rather, acceleration must be bigger than some critical accelerations, which depend spatially on radial distance. Thus, the inequality becomes easier to satisfy at large radial distances, in which case the acceleration is indeed quite small, as MOND suggests. Let's look at the mass accretion model. So I take a very simple model. Yes. And you can calculate Euler equations. And I suppose a dynamical equilibrium, so velocity is constant from below and above. Some initial mass density profile. This is the galaxy, and this is how it falls in, perpendicular to the galaxy. And it's solved analytically. You can calculate the mass outside the galaxy, and from this you can know how, because the total mass is conserved, how much mass is inside the galaxy. So you have m dot, m double dot. M double dot seems to be in this analytical expression. Vz is the velocity, and k is of course related to the gradient of the density profile. Okay, so m dot, m, etc. Some results for galaxies, some done by myself. In this case, m over L is 1, meaning that I didn't play with this parameter at all. This is the m double dot. This is by my PhD student, Michal Wagman, who did quite a lot of those. Those are her results. Tomer Zimmerman and Roy Gommel also worked on this. And Yuval Glass, which is my recent student, has automated the process. So now he can do 143 galaxies with his program in 20 minutes. So you can see some results from his calculations. Okay. Now, there's a lot of things to show, but I was not given enough time. So I'll just skip to the end of this and discuss the relation between retardation and MOND. Okay, so this is a famous equation of MOND. And there is an interpolation function, which is arbitrary choice. There is a standard choice. This is the standard interpolation function. And In the deep Mondian regime, mu is A over A naught, and you can calculate and you get this equation. If you believe that this is due to retardation, you equate the two forces and you get this. And this is useful. I mean, you can put A0, MW dot you get from the rotation curve, and then you can calculate, for example, the typical time scale and the typical retardation distance, which is somewhat interesting. It's about here. But of course, this cannot be taken very seriously because m double dot is constant, and this goes like 1 over r. So a better thing to do is to take a non-standard interpolation function, which is x squared over square root of 1 to x to the 4th, and then you divide and you get this equation. And when you do this, you get a mu which is a to the a0 over square, and you get this equation. This makes more sense because now you get this equation for m double dot. It gives you a Tully-Fisher relation immediately with this constant. And of course, you can calculate A0. So A0 is not like a constant of nature, but something which you can fit to the system that you study, which can be a galaxy, a cluster of galaxies, etc. And then if you do this, you see that MOND retardation theory is a MOND type theory in which the Mondian field is equal to the F Newtonian plus the retardation correction, but there is a non-standard interpolation function. So I didn't show everything, but you can read in the papers: rotation curves, lensing effect, Tully-Fisher, coma cluster, virial high velocity, etc. And you can do this with no exotic matter and no modification to gravity. And retardation theory can be approximated as a MOND type theory with a non-standard interpolation function. Things like MG1052, DF2, and DF4 are easy to solve because m double dot is probably just 0 over there. And let's conclude by quoting Einstein again. The load is subtle, but melicity is not. And retardation effects are indeed subtle. Of course, you should always beware of the dark side. And we are looking forward to the next 40 years of MOND. Thank you.
It's very late. I think we'll also have a discussion of this paper. All this is a general discussion.
No problem.
That's it.